Assalamu alaikum. Myself Khadija Jabbar and my roll number is 37 and I am from the Department of BS Biotechnology. And our presentation topic is Raman spectroscopy. And I am here to present the instrumentation of Raman system. First of all, we'll discuss the history of instrumentation. Modern Raman spectroscopy nearly always involves the use of lasers as excitation light sources. Because lasers were not available until more than 3 decades after the discovery of the effect. Raman and Krishna used a mercury lamp and photographic plates to record spectra. Early spectra took hours or even days to acquire due to weak light sources, poor sensitivity of the detectors, and the weak Raman scattering cross sections of the most materials. Various color filters and chemical solutions were used to select certain wavelength regions for excitation and detection, but the photographic spectra were still dominated by a broad center line corresponding to a Rayleigh scattering of the excitation source. Components of the Raman system. There are following components involved: excitation source, sample illumination system and light collection optics, wavelength selector and radiation transducer, detector, which is a photodiode array, and CCD or PMT. Then we'll discuss about detectors, detectors for dispersive Raman and detectors for FT Raman. So this is the basic instrumentation of the Raman system: laser source, and then sample cell, wavelength selector, radiation transducer, and then the CCD, which is a detector. What is a laser source of light? So basically, lasers operate using the principle of stimulated emission. Lasers are generally the only source strong enough to scatter loads of light and lead to detectable Raman scattering. So basically, in Raman spectroscopy requires a light source such as a laser. The resolution of the spectrum relies on the bandwidth of the laser source used. Generally, shorter wavelength lasers give shorter Raman scattering due to the V4 increase in Raman scattering cross sections, but issues with the sample degradation or fluorescence may result. Wavelength selector and transducer. So, for getting monochromatic radiation, filters are used. They may be made of nickel oxide glass or quartz glass. Continuous wave lasers are most common for normal Raman spectroscopy, but pulsed lasers may also be used. These often have wider bandwidths than their CW counterparts, but are very useful for other forms of Raman spectroscopy, such as transient, time resolved, and resonance Raman. Sample holder. Any solvent which is suitable for the ultraviolet spectra can be used for the study of Raman spectra. Water is regarded as a good solvent for the study of inorganic compounds in Raman spectroscopy, and in this way laser passes the sample holder. The sample of Raman spectroscopy may be solid, liquid, or gases. Solid sample. Raman spectra of solid samples are often acquired by filling a small cavity with the sample after it has been ground to a fine powder. Polymers can usually be examined directly with no sample pre-treatment. Liquid samples. The major advantage of the handling in Raman spectroscopy compared with the infrared arises because water is a weak Raman scatter but a strong absorber of infrared radiation. These aqueous solutions can be studied by Raman spectroscopy but not by infrared spectroscopy. Gas samples. Gases are normally contained in glass tubes 1 to 2 centimeter in diameter and about 1 millimeter thick. Gases can also be sealed in small capillary tubes. Raman spectrometers. So Raman spectrometers were similar in design and used the same type of components as the classical ultraviolet visible dispersing instruments. Most employed double grading system to minimize the spurious radiation reaching the transducer. Photomultipliers served as the transducers. Now, Raman spectrometers being marketed are either Fourier transform instruments equipped with cooled germanium transducers or channel instruments based upon charge coupled devices. Detectors. Nowadays, multi-channel detectors like photodiode arrays, charge coupled device, sensitivity and performance of modern CCD detectors are high. These are the diagram of the modern detectors. In most cases, modern Raman spectrometers use array detectors such as CCDs. Various types of CCDs exist which are optimized for different wavelength ranges. Intensified CCDs can be used for very weak signals and or pulse lasers. The spectral range depends on the size of the CCDs and the focal length of the spectrograph used. Then we will discuss about the detectors for dispersive Raman. In most cases, modern Raman spectrometers use array detectors such as CCDs. Various types of CCDs exist which are optimized for different wavelength ranges. Intensified CCDs can be used for weak signals or under pulse lasers. The spectral range depends on the size of CCDs and the focal length of the spectrograph used. It was common to use monochromators coupled to photomultiplier tubes. In this case, the monochromator would need to be moved in order to scan through a spectral range. Detectors for FT Raman. FT Raman is almost always used in NIR lasers, and appropriate detectors must be used depending on the exciting wavelength. Germanium or indium, gallium arsenide detectors are commonly used. This is the schematic diagram of FT Raman. And this is the laser and lens samples, then Michelson interferometer, dielectric filter, foxing mirror, and liquid and to cool detector, as you can see in this diagram. So in now we'll discuss the basic technique of the instrumentation. This figure illustrates a typical Raman spectrometer. The laser beam is passed through a cell, usually a narrow glass or quartz tube filled with the sample. Light scattered sideways from the sample is collected by a lens and passed into a grating monochromatic similar to that used in a dispersive infrared instrument. The signal is measured by a sensitive photomultiplier, and after amplification, it is usually processed by a computer which plots the Raman spectrum. The use of plain polarized radiation gives the information about the symmetries of molecular vibrations. To make these measurements, the laser beam is plane polarized perpendicularly to the plane of the paper, and a polarizing filter is placed between the sample and the collecting lens. The Raman spectrum is then measured twice. First, with the polarizing filter set to the pass side polarized perpendicularly to the paper, and then at the right angles to this. The polarization of that line for vibrational measurements, the Raman technique has several advantages over infrared spectroscopy. Firstly, because both the incident and scatter radiation are at ultraviolet or visible frequency convention optics and same cells can be used. So avoiding the problems inherent in NaCl windows, atmospheric absorption, etc. So, secondly, because the beam can be focused extremely finely, very small samples can be studied. This combined with the pulse techniques, which can give very short time resolutions, enables very small quantities of transient species to be studied. And thirdly, water which has a strong infrared absorption is a rather weak Raman scatter, and so aqueous solutions can be studied using the Raman spectroscopy because the sample signal is not swamped by that of the solvent. These reasons collectively ensure that Raman spectroscopy is particularly well satisfied to the study of biological systems. For example, it can be used in the study of the spectrum of myoglobin. So that's all from my side. Thank you so much.